Hi, it's Teardown Tuesday again. This time around, I've got something big and beefy. It's a Xantrex 300 volt, 4 amp, 1200 watt, 1 rack unit power supply. Ha ha ha, lots of high energy stuff. I love it. Let's check it out. Now the unit we've got here is the Xantrex XFR300-4, and it actually comes in a whole bunch of different models from 0 to 6 volts at 0 to 200 amps, right up to 0 to 600 volts at 0 to 2 amps. So this one is the second highest. They're all 1200 watts, but this one's 0 to 300 volts DC output with 0 to 4 amps. Beautiful. And of course these aren't bench power supplies at all. These are designed to go into racks. This is a 1 rack unit high, and all the voltage and current knobs are on the front, and the power switch is on the front, and a few other miscellaneous function buttons, but all the power output and power input is on the back because they're designed to wire into big rack mount power systems which could power anything custom. So even the power cord, even though we've got a standard power cord on here, you'll find it's not a standard IEC input connector because these things aren't designed for just general purpose consumer use. And on the back here you can see there's a whole bunch of these Phoenix input connectors, and you can see that it's really centered around remote operation. There's various sense lines and remote programming, so you can program the current and voltage with external resistors or external pots or or you can do it using digital control or whatever. These are very flexible power supplies designed for system use. And if we pan over here, we'll see that there's the output voltage there. It's another Phoenix terminal block in there with a safety guard on it because these things are high voltage outputs. And there's the mains input there. It's inside a block, but once again you've got terminal blocks in there to actually screw that in. There's a big strain relief here, but you can actually wire in your cable in, your mains input cable in directly into the unit. And here's something you don't see every day, made in Canada. Beautiful. Sorry, I don't know the Canadian national anthem. If I did, I'd sing it. Bring a tear to the eye of my Canadian viewers. And you know what we say here on the EEVblog, don't turn it on, take it apart. But there's a very good reason why you don't want to switch these things on before you take them apart, because lots of high voltage, high energy storage caps in here, so you really want to let those discharge before you take apart something like this. And any well-designed supply like this Xantrex one, top quality industry reputable brand, I'm sure it's got discharge bleed resistors in there. And here we go, let's lift up the skirt on this thing, and you can expect some big electrolytic caps, and quite a few of them, probably half a dozen or a dozen, and you can expect some big ass inductors and lots of stuff like that, plus some control boards. So ta-da! Oh yes, look at that. Oh, let's check it out. Oh, and it really doesn't disappoint, does it? Check it out. We've got one huge mother of a PCB on the whole thing. We've got, it looks like some digital control board over here. You can tell by the packages there. We've got our front panel board, but oh, look at this big power supply. Like I said, a whole bunch of electrolytic caps, high voltage, high value caps for storing the DC, because what this basically does is convert your AC straight into DC, and then it's basically a DC to DC converter after that. So you've got a whole bunch of EMI input inductors here, you've got input relays, we've got heatsink, and we'll check out these devices later. We've got 3 fans up here. That's rather interesting placement for the fans, actually. Usually you would have them, might have them on the back panel here or something like that, but there's a big grill on the back. But yeah, that's rather interesting. They're going through there. There's some cardboard under there. We'll check out. In fact, that's a whole cardboard piece actually going, square piece going right around there, just sort of separating things a bit, and it goes through here like this. And but yeah, we've got our big power devices here, a couple of transformers, and miscellaneous stuff. Actually, I stand corrected. It's not one huge PCB. If you actually get in and look at the details, there's one large input filter board here, which basically converts the 240 volts or the mains into DC, into high voltage DC. And then we've got the second board here, which looks like your basically your high power DC to DC converter board. There's another miscellaneous control board here with a whole bunch of sort of analogy type stuff, plus your digital board. And let's start out with our mains input circuitry here and have a look to see what's happening. Now, what we've got here, here's our terminal block input, 2 HRC fuses, just like you'd see in a multimeter, high rupture capacity fuses. Then we've got a whole bunch of EMI stuff. We've got 2 MOVs here by the looks of it. We've got 2 relays. I'm not sure what the relays are switching in and out. Maybe it's you know, software controlled. It's like a soft start power on or something to that effect. And a couple of big power resistor there. A smaller fuse there. I'm not sure what that one's doing. And some mains rated self-healing caps here. And this is pretty much just EMI filtering so that it just keeps the noise from escaping back out the main supply. And here's our bridge rectifier, because this is an AC to DC converter, so that takes the 240 volt or 110 volt mains input and converts it directly through a full wave bridge rectifier, as you're familiar with. But this here looks like it might be like an earth terminal or something, but let's take a closer look at that one. And of course a big heatsink here for the bridge rectifier, and you can see the white heatsink compound in there as well. Now if I take these 2 blade terminal wires off here that go through to the main switch on the front panel, you can see the wiring in there coming from this here, and it looks like cable, but it's not. It's a dual wire thing going into a little splice terminal block there, which insulation displacement splice terminal. So there's obviously, that's some sort of thermocouple that's measuring the temperature of the bridge rectifier. So they've put, you know, they're not just rectifying this and just be done with it. They're actually monitoring the temperature, so presumably they can shut this thing down if it overloads. Yep, you beauty, it's Dave CAD time. Please excuse the crudity of the model, didn't have time to build it to scale or to paint it, but this schematic here represents what I think is happening on this board, and it will map, this schematic will map to the physical components down here as we go along. And I'll try and explain that. I haven't actually traced it out, so it won't be may not be 100% accurate, but it's pretty obvious what's going on by the physical location of the components and based on some basic theory of how common mode input, EMI, chokes and things work. What we've got is our mains input over here. We've got our 2 HRC fuses here. We've got our common mode, this is a multi-stage common mode choke. So here's the common mode choke with, we've got a filter cap there. Here's our common mode choke. There's the ferrite, and with the top winding and the bottom winding there. Then these 2 grey caps here and here, these go to earth. And then we've got another common mode choke here. Once again, the top winding, the bottom winding there, going in this time a parallel filter cap. And then we've got 2 big MOVs here and here, because there's 2 of them. I'm fairly certain, without having to trace it out, that they will go down to earth like that. And then you may not be able to see that in there, but there's a tiny little 1/2 watt axial resistor in there. That's actually 1 meg, and as I mentioned at the start, that's a 1 meg bleeder resistor, just to bleed off any voltage stored on these caps. And then we've got another well, it's not a common mode choke this time. We've got 2 separate inductors here and here, and then we've got another parallel filter cap, and then another MOV. In this case, it will be in parallel and go directly across instead of to mains earth. I almost forgot these 2 little inductors, 2 extra inductors here and here, so that's another stage of filtering. And then we'll talk about this soft start in a second, but then it basically goes into the bridge rectifier, which converts the AC input into DC. So all this stuff we saw is just for EMI filtering, and well, they've really gone to town on that one, and also overload protection with the MOVs. So the standard bridge rectifier here, which is on the big heatsink like this and temperature monitored, as we said, converts the 240 volts or 110 volt AC into DC. And these are our main filter caps here. There's actually 10 of them. There's a few more off camera here. And I looked at them and I saw that they were only 1000 microfarad, 200 volt. So I went, well, that's not high enough to put them directly parallel across here, because if you convert 240 volt mains into DC, you're going to have higher than 200 volts. So clearly, because they've got them in pairs like this, what they've done is, this is not unusual at all, they've put them in series like this to effectively give you a 500 microfarad, because it's half the value, at 400 volts instead of 1000 microfarad, 200 volts. And they've done that 5 times. So effectively, they're able to create a larger voltage electrolytic filter cap with 2 lower voltage units. But if you've seen my capacitor tutorial, you know that's not necessarily a good thing, because when these things age and get old, or they're mismatched from the factory, they may not share the voltage. You know, you may not get 200 volts across there and 200 volts across the bottom half as well. So that's why there's 2 resistors here. There's a big, looks like a 5 watt, it's actually 10K, and there's another one here. So that clearly shows that these are current sharing resistors, because that will just help keep this voltage at the center, especially when it first powers up, to equally share the voltage across these caps. And now, this soft start circuit, as I mentioned, that's what this big resistor over here is doing, I think. It's a 15 ohm, 13 watt resistor, massive power one, and there's 2 relays here, so I'm not sure exactly the configuration, but let's just say there's one relay. I'm pretty sure it's just going to short out this 15 ohm resistor, because when you first switch this thing on, these capacitors are going to be discharged, and they're going to go, and they're going to suck in all the current. You're going to have a huge current surge through your diode bridge into your capacitors, and, well, that's not such a good thing. So that's why they put the series resistor in here, surge protection when you first turned it on. The relay's unenergized, so you've got the series resistor, which limits the inrush current to the capacitor bank. And then after a couple of seconds, determined by this control circuitry or something else down there, then it switches on the relay, shorts it out, and bingo, you can start operation. And we get our high voltage DC output directly across the filter caps. And bingo, that's all there is to it. It's pretty basic. There's nothing unusual or surprising there at all. And there's a bit of control circuitry down there. It's probably an op amp or comparator or something like that. And it's obviously, maybe it's doing some extra, mains failure protection or mains failure detection or something like that, perhaps, which might automatically, there might be another relay to automatically switch off the power there. But there you go. It's a pretty basic operation, but because it's big and high power, that's why you need a huge board this big. You need the massive inductors, the big filter caps, the big filter capacitors, the big MOVs, and really it takes up a lot of room. And you can actually see this ribbon cable here going from this mains input board over here somewhere. So that's obviously, to control the mains failure input detection or something like that. There may be a bit more, maybe it can measure it or do something like that perhaps. But clearly they've linked that over here, and it does some control. And our high voltage DC output here goes over here up into this board here. Let's take a look at that one. And if we peel back some of this protection cardboard here, we can see the high voltage DC from our supply board coming into here. We've got another filter cap by the looks of it, and we've got 4 huge devices mounted on this heatsink, which has the 3 fans. Basically, it's probably, it sucks air from the sides of the unit, and I'm not sure which way they're blowing. They're probably blowing out that way, and well, they would be. They'd be blowing across these heatsinks here and out the back. And these four devices are high voltage, high current N-channel MOSFETs. They're IRF P460s, and you can see we've got some temperature sensing coming off here as well in exactly the same crimp configuration that we had for our mains input. And take a look at this. You'll notice that these screws here, it's an interesting method to join this board through to this board. They've actually got these big screw studs here, which actually are the high current interface connector between these two boards like this. Beautiful. And what we've got here is a UC3875 phase shift resonant controller, and it controls the four N-channel MOSFETs up here. And if you have a look at the data sheet for that, you can see the output configuration with the four MOSFETs. And also we've got two IR 2110 high side MOSFET drivers. And then we've got our power also going over here via this twisted pair cable into another heatsink device with a whole bunch of power MOSFETs and the switching transformers and another choke in there by the looks of it. And it may be hard to see that, but these transformers are actually mounted on their own PCB, which sits flush with the other PCB. You can see the breakout tabs there from the PCB panel. And here's the output side of things. We've got two big 400 volt this time, 330 microfarad caps. Looks like there's some there's position for another couple of caps there. Interestingly, this one has a big jumper on it going across the cap like that. So, and here's our output terminal over here. We've got some output protection and a little bit of control circuitry around there, but that's probably about it. And what I thought was output protection there perhaps is not, it's not. These are output filter caps. They're a Z5U dielectric. It says there 1 kilovolts at 0.05 microfarads. Now there's a couple of these devices on the board. These are very interesting. They're actually a 105K, that's 1 microfarad, of course, 400 volts. It looks like they're metallized polyester capacitors. I think it's worth digging up the data sheet on these. They've got one of them there, and also they've got two of them up on the input side of the board over here. And here they are. They're made by a company called Pactron, and they're metallized polyester PET dielectric. They call them capstick capacitors, and they're basically ultra high reliability, high MTBF capacitors, and made in the US of A, Star Spangled Banner. I love it. And they're for high ripple current, high capacitance, high frequency switch mode, DC to DC. Converters, and they're high reliability. And it says, like all film capacitors, capstick capacitors have true voltage ratings, and unlike other dielectric systems, require no voltage derating for maximum reliability. Excellent. This is exciting stuff. There you go. So, it tells you many leading-edge circuit designs take advantage of a film capacitor's inherent reliability at rated voltage to reduce board size and improve performance. Well, I don't think they were going for board size here in this huge one rack unit case, but there you go. These are little interesting beasts here. They're obviously multi-pin to get a lower inductance in there. So if we scroll down here and take a look at some of the specs, they range from 0.33 microfarads up to 20 mic. We're using 105s, which are 1 microfarad. This gives you the lowdown. Miniaturized pass filters made possible by high-frequency switching technology need tiny but low ESR and low ESL capacitors to attenuate ripple and reflected RFI over wide frequency bands, with equivalent series resistance approaching 0. Excellent! Non-polar MLP capacitors reliably sync high ripple currents in high-density converters, run cool, and are stable. Ooh, what's not to like? But I'm sure these things aren't cheap. You probably pay easily a couple of bucks each for these caps, I'm sure. Maybe even $10, who knows? That's why these things are mega expensive, these types of power supplies. And we've got some more temperature sensing action down here. Once again, exactly the same crimped configuration as before. And we've got some extra chokes here. There are only a couple of turns on the ferrites. And these look like ceramic thick film resistors. Silly me, I should have looked at the number of legs on these. These aren't MOSFETs, these are actually diodes. They're an Ixus DSE 130. Can't find any info on them, but presumably very high power and probably quite expensive. And there's nothing to write home about on the front panel here. Pretty basic 7-segment LED display interface with the sockets, just putting them out a set distance. Basic standoff construction with the big 40-pin dip. No surprises. ICL 7107. And we have some calibration adjustment pots here. They've been gunked up with the red set, so someone has put their tongue at the right angle, tweaked those, and then set those down so vibration doesn't affect them. And standard LED standoffs there, some basic push-button switches, and the 10-turn pots for the voltage and current controls. And after all this awesome power stuff, I think the digital side's a bit of a letdown, but what the hell, we'll check it out anyway to see what processor it's actually using. Nothing exciting, I'm sure it's very old school, but we'll check it out nonetheless. And let's see, does it pop off? Oh, no, we've got to undo the jack screws for the D9. Now this board here is actually the optional remote control board, so you don't get this in the standard configuration, but bingo, there it is. It might be upside down, but there it is, made in Canada. Interface card, brilliant. Very old school disc ceramics, just bent over like this, all crowded in there. Quite old school, I love it. Fox crystal. We've got a ROM here and a local regulator and a PLCC package processor. You don't see PLCC packages in sockets too much these days. Not too many surprises, it's a Motorola MC68HC11. But of course it seems to be dual processor because there's another second 68HC11 as well. We've got another ROM up here, so there's two ROMs, probably an interface and control or something like that. We've got a DAC up here and not much else. So that's the interface board, couple of miscellaneous 74HC series circuitry, but yeah, not much happening there. And here's the Phoenix connector inputs. There's some jumpers here and once again a bunch of 10-turn trim pots there, and they're set with the red gunk. And there's things like iMonitor, uMonitor, iProgram, uProgram, and they're set. And here's the Phoenix input connectors down here, which control the voltage and current remotely. Not exactly sure what this daughter board here is doing. It's got a trim pot on it and a couple of op amps and things like that. So yeah, they've put that as a secondary board, just basically sitting on top of the other one, directly soldered onto the main board. And basically that's all the control stuff inside this. If you ignore the optional interface board, then this is all your remote programming voltage stuff, which controls your main DC to DC converter in here. Here's your DC input board up the top. It comes in here and it goes across. This is your main high frequency DC to DC converter section. Some output filtering, and it goes straight to the output over here. And this circuitry just controls it with some display stuff and miscellaneous power stuff over there. Too easy. So there you go. That's the Xantrex XFR300 300 volt 4 amp power supply, and it's a really top shelf brand, huge quality industrial designed, properly designed system rack mount power supply. I was pretty darn impressed. It was basically they're spared no expense in this thing. It's all uses prime top shelf components, really well designed, really laid out, really modular. A lot of thought's gone into these. Really pros have designed this. It'll be very high reliability, and you'll pay for that sort of stuff too. So I hope you like that. I certainly did. It was very interesting. So remember, if you like Teardown Tuesday, give the video a thumbs up. It helps a lot. And if you've got any theory and ideas about how exactly all of this DC to DC converter works, jump on over to the EEVblog forum and discuss it, because this sort of stuff, very interesting. Catch you next time.